Okay, let me continue. Okay, now we continue with our lecture. So in the today morning session, so we have a discussion about the time variation of a channel and frequency variation of a channel. And I have introduced two correlation function of the channel. Namely, you have a time correlation function and frequency correlation function. In the time correlation function, it's a measure of the variation of the channel in the time domain. And we have two cases. The first case is that the current path is much larger than the simple duration. Then we have a time invariant channel. And in the other case, the coherent time is much more smaller than the coherent duration. Then we have a time variant channel. So that is in the morning utilization we have discussed. And in the time invariant channel, the channel is nearly flat in the time domain. It's nearly flat in the time domain. Here, it's in the case that if the channel is time invariant, then the channel is nearly flat in the time domain. And if the channel is time varying channel, then the channel is frequency this time selective. And if the channel is non-frequency selective channel, then the channel is flat in the frequency domain. Yeah. And if the channel is frequency selective, then the channel is faded in the frequency domain. So that is we are not discussing about the variation of the channel in the frequency and time domain. And today afternoon session, we continue with the wireless channel. And next, I introduce you two typical channel model, or two typical channel that appear very frequently in the wireless channel communication. The first is ready channel, and the second is the right channel. And they are very popular. And they are very popular in wireless communication, and even with the simulation model, we usually consider these two typical cases of the channel. So in this session, we introduce you. I will introduce you these two channel model when it appears, and how is the statistical distribution of the channel. In the wireless channel, in the wireless communication, there are two typical cases that appear in the communication. And the first case that you know that there is no line of sight component. Not possible to recognize the anyway, it's very wrong. So that's good idea. I think not possible. Okay. So after the end of the lecture, we just make a picture together. So that should be sufficient. Okay, let's continue. We have a radar channel. When it appears, you know that in the transmission environment, there is no life science connection. Suppose that we have a mobile phone, and the base station is somewhere outside. We still receive a good signal, but in this case there is no luminance component. There is no life science. Life science has direct connection. And the reflection from all the directions, they are similar. They have a same power. They have a same power of the receiver power. And in this case, the channel has the distribution function follows the radar distribution. Follow the radar distribution. And we call that radio channel. Radio channel. And here is the mathematical description of the telephone response. And we suppose that there is no line of sight of the transmission in the transmitter and receiver. There is no luminance path. And the mobile antenna receives a larger number of reflected discuss well, it means that they receive signal from a large direction. And in this case, we have the channel is complete. The channel is complete with the baseband here distribution. And the real part and the imaginary part, they follow the Gaussian distribution. And their amplitude will follow the radial distribution. That's why we call this channel radial. And I show you how it looks. How it looks. So in this this is the run time of the channel, amplitude of the channel. So I have a give you a software so that you can create the channel. I have a give you a software so you can put on the desktop and you can run it. And you can also simulate the channel. So that's very easy to simulate. Can do it yeah. And you observe the amplitude of the channel. Yeah. And here is the runtime of the amplitude of the channel. So in this earlier, the channel is faded, strongly faded. And the answer, they are okay. Okay. It means that it has below, it's above the progress region. And we can compute the distribution of the amplitude of the channel. We can compute the probability density function of the channel and we can also calculate based on the theory and compare to each other. And I show you the results. Wait. This is the simulation results. Later on, I will also give a code for you, and you can also simulate it and so locate the results. I will show you how to obtain this calculation. One is one is a simulation, and the other is a theory. And this follows the Rayleigh distribution of the channel, the simulation and the theory calculation. And where it comes from this distribution? Yes, that is runtime. And now you need to compute the distribution function of this of the amplitude of the channel. And the easy result is the distribution the distribution results. And so the last reverse line. And here is the theory. The theory from the Broadcast book. So I just let's say rewrite it from Broadcast book, and that's the theory. And we compare the theory with the simulation results. Let's show you. That's the results, yeah. And wait me 1 second. I show you an exercise. I show exercise. I can also give you a copy of this. Actually, that's my book. So that's my book. I can make a copy for you, so you will have as a soft copy. I just show you one of my exercise, so that you can simulate the you can simulate the relay channel. So that is exercise number 4. Can you the homework? Yeah, exercise number 4. Homework exercise. So you can exercise number 4. Number 4. So page don't know. Exercise number 4. I explain for you. Very short. So you need to read at home. So actually, in the next slide, I will teach you how to model the channel. And that this is exercise. I introduce you how to model the relay channel, relay channel by using the method. And the theory is so in this exercise. So I will not go deeply in detail, but actually you can model the channel by using the discriminative function. It means that that is the amplitude of the channel. Amplitude of channel. And the amplitude is a summation of the two parts. One is the it's not really the amplitude. The summation. This amplitude is another need to be the square of the you need to compute. First, you need to compute the real part, and then you need to compute the imaginary part, and then you need to take amplitude of the complex value, and then this will result in the amplitude of the channel. And in this simulator, you need to also calculate some parameter. I think you can read at home. So because it's quite a lot of information, I will make a copy for you. So it's somehow like you need to calculate this parameter, and then you work on this simulator, and then you can let's say you can simulate the relay channel. I think that's my lab code, etc. Yeah, the exercise. Yeah. Oh. Yeah. So that's a relay distribution. One is a theory, and the other is a simulation result. So I just make a copy from this simulation result, or I need to make a copy of this result to my slide. No more. Okay. Okay. And here, in this distribution, you will observe that the signal is higher amplitude. They don't suffer from the decay. However, if the signal is if the signal having a low, very low amplitude, then it suffer from inference. And this case, it introduces the so-called error bus. Yeah. Link this results to other figure here. This the signal have a lower amplitude, so this introduces the error bus. Yeah. errors. And the answer page, there's no problem. Okay. Okay. So that is the relay channel. Relay channel. Yeah. So relay channel, I repeat again, relay channel is kind of when there's no direct component, and we have a large number of the receiver signal, and they are equal of the power, receiver power. So they are equal of the receiver power. And in this case, the amplitude of the channel follows the Rayleigh distribution. And in some book that I will give you later, in the exercise, I teach you also how to simulate the channel. Yeah. You can also calculate based on the equation, and also you can simulate the channel by using the computer simulation and you can compare together, and you can see that they fit well together. That's actually that is exercise number 4. Now we okay. Now I skip this slide. Okay. Now we move to other channel. So it's called so-called right channel. Right channel. In right channel, is also a typical case. Let's say we see that here's microphone and there is the receiver antenna. There is a direct component and a lifetime component. And if we have a lifetime component, then the distribution function of the amplitude received signal will not follow the Rayleigh distribution. Instead, it follows the Rice distribution. Yeah, it follows the Rice distribution. And actually, the difference is only because there is there is the direct the lifetime signal or the direct connection. So the distribution of the amplitude of channel change, and it follows the Rice distribution. So no more difference. So it's actually also easy to understand. Yeah. Okay. Now we move to the next section. I think this section is a little bit handy to understand. Not a little bit it's a little bit difficult with the mathematical distribution. But I hope that you will not get bored because heavy calculation. So I will help you to understand. Actually, there is a very good paper writing about this theory. I'm sorry. No, this is not here. Yeah. Oh no, that's not here. So there is a good publication writing about this topic, and I remember that is the paper of Bello. Yeah. So he writing a paper about 40 pages public IDE information theory, and there deeply describe about the mathematical description of the channel theory. So I'm not trying to short and summarize this paper and speak to you. And that is today morning section we have discussed about the correlation function of the channel. Correlation function of the channel. Yeah. So what is the correlation function? I think you have a study in the background course. Maybe start this figure communication or scientific background. Somehow, like I suppose that we have studied about the person. So my question to you that what is what is the correlation function, and what's the purpose of correlation function, and what is used in the theory of the quality computation. So we are talking quite a lot about the correlation function, right? Correlation function. What it is and why we use correlation. What's the purpose? We use correlation function. So what is the statistical character of channel we can describe by using the correlation function? So if someone of can let's say explain to our class something maybe about the idea about understanding about correlation. Cross correlation and on correlation. They are correlated. They have a correlation rate. Yeah. Even uncorrelated, so it's very zero, right? So in this case, we can see that we can use this. It's more easy to understand that if they are correlated. Some say if something they are correlated, the other if they are somehow similar to each other. So if I'm talking to the class, you and me, we are collaborated, and somehow that you and me are independent. So you are not my son, you are not my student, you are not my brother, yeah? We don't know each other. You are not. So we are isolated. I'm even though I don't care how old I am, we are isolated. We are what? We are connected. We have a connection. Some similar, some aspect. We are what? For example, you remember listening, discussing. We are living correlated. We are what? Because we come from Vietnam. Yeah? So we speak the same language. That's something a little correlated. Yeah? That means that I don't follow on. At least we are a little bit correlated. But we are uncorrelated. We are totally different. We are not independent. Yeah? So if the signal when we are working on the synchronization, yeah, we need to detect the variable of the signal, yeah, and we need to detect the peak correlation peak. You get the point? And in this case, if the signal they are correlated, they are well correlated, so it charges for me to detect the variable. Or it charges to synchronize. The variable is not somehow like bios signal. We just pick up the variable below it, below the charge signal, below the signal. So after travel at one correlation, get some specific correlation. So we detect this correlation by using the variable. Then we see a bit. And this is and in the wireless channel, the autocorrelation tells us about the variation of the channel. As I tell you in the beginning. It means that if the channel, so they vary very fast. Yeah. They vary very fast. We check very fast. So they are really uncorrected. If we shift the signal to between the part of the picture, they are correct, they are uncorrected. And if they are uncorrected, yeah. So yeah. If they are uncorrected, that's the correlation comes in. If they are uncorrected, then it becomes complete. No shape. They come with peak. Yeah. So if they are very correlated, so it's like this. And if they are very correlated, uncorrelated, so it's become a peak. So if they are if the channel if the channel if the channel say having a very wide, yeah, very wide, there's let's say if the that is a coherent bandwidth. That's the coherent bandwidth. Yeah. That's the equals of the maximum time delay. Okay? Certified by 4. Yeah. And if the channel very fastly, you get the point? Then if the channel very fastly, normally that's the case when how much is become large. Yeah. Then this should be small. And you have this bandwidth, it becomes small, and it becomes big. You get the point? So if the channel has a very long time delay, then the coherent bandwidth becomes very short. The bandwidth of the coherent is also very short. Yeah. And if you travel with a rocket, then this becomes big. And this case, the channel is strongly very or the channel very fast. Yeah. And if the time delay is very short, so it means that we are working in the indoor communication. Yeah. The communication distance is very short. And you have a last you have a big you have a more broader bandwidth of the coherent, the bandwidth of coherent. It means that this function becomes larger. In this case, the channel is slowly, very slowly. And now you know that correlation function tell us about the variation of the channel that we have learned today this morning. I repeat again. Now you know that the purpose of the correlation it tell us about it tells us about if the channel is correlated or not correlated. You can use to increase the dipole channel capacity. You can use to detect to summarize the signal to detect the correlation bit, as he said, correlation bit, and you can use to know if the channel very fastly or just if the channel is time invariant channel or if the channel is time variant channel. So that's the overall correlation. So if you hear about correlation, you hear repeat again and again and again. Many lecture goes to come they tell us about correlation, but we need to understand deeply and what's the sense. The deeply basic concept of the correlation. And that's what we're talking about, the physical content. Yeah? But now we need to work a little bit with the mathematical description, how it's, so it's more a little bit difficult. But actually, I have a prepared slide for you. Here. That's the definition. Now we try. Not easy, very difficult, boring actually, with a calculation. But now we are starting with the definition. So the definition is very simple. But actually not only the expectation of the channel response, which is observed is tau 2 and T2. So it's observed is the time delay tau 2 and the observed time tau T2. So you multiply with the channel, also the channel response with the conjugate. You know what is conjugate? Yeah. That is in mathematical description. The definition. And now we suppose that the channel is a Y-channel stationary channel model. So this is also described in the many books. Yeah, it's by background. So if the channel is Y-channel stationary, so you can replace tau T1 by T and T2 by T plus delta T. The meaning of this replacement that we observe the channel, the observation results does not depend on the observed time. That depend on the observation duration. You get the point? So it means that like somehow like you observe the channel, so it's observe traffic on the road, or you observe a river, the river, yeah. So you can observe in the morning, or you can observe in the afternoon, or you can observe in the evening. But the observation results does not depend on the time what we are going to observe. Does not depend on the time that you are going to measure. It depends on the duration of the so that's the assumption of the Y-channel stationary channel. That assumption. Yeah. So in this case, we can replace T1 by T, T2 by T plus delta T. In this case, we can derive from this equation to this equation. So by replacing T by T2 by delta T, T2 and T1 by delta T and T2 by the T plus delta T. So in this case, we replace T1 by T, T2 by T plus delta T, and we have this replacement. So that is the one replacement. And the other more assumption that the channel is wireless stationary and uncorrelated scattering channel model. So we call that is the WSSUS channel model. And this channel model, we suppose that the part of the channel, they are uncorrelated. Yeah. They are uncorrelated. It means that they are statistically independent. Yeah. So it means that the right part and the reflection part, they are does not relate to each other. They are totally different and they are independent. That is uncorrelated channel. Means this. And this is it with it assumption. With the second assumption, it means that uncorrelated scattering. So we can bring this equation to this one. It means that we can replace by x tau 1 and x tau 2 by the function of delta tau 1 minus tau 2. And in the simulation, this model is commonly used for simulation. And what we can drive more here is, suppose that we observe for the delta is equal to 0. Yeah, delta equal to 0. Then we can go to the results. The correlation function of the channel for one time delay and for the observation is equal to 0. Then it's equal to the expectation of the channel impulse response. Yeah. And its result is the rho tau. And rho tau, that is the channel delay profile. That is channel delay profile. Okay? Channel delay profile. I think it's a little bit heavy, but I try to help you to understand. Now we have I have introduced to you the correlation function of the channel impulse response. Yeah. Now we go to the auto correlation function of the channel transfer function. Yeah. There are two keywords. One is the channel impulse response, and the other is the channel transfer function. Okay, and they are connected by the Fourier transform. Okay, they are connected by Fourier transform. And we observe the channel transfer function of the y stationary channel here. Similar to the definition of the autocorrelation function of the channel impulse response. So we can also define the correlation function of the channel transfer function. And you know that the definition is the same. It's the same. That is also the expectation of the transfer function of the channel observed with the frequency 2 and at the time t plus delta t. And here is the frequency omega 1 at the time t with the conjugate coupling. Okay. And that's the definition. Yeah. And now we need to replace the transfer function by the channel impulse response. Yeah. And you know that we have a relation or interrelation. H F T equal integration X tau T is R E G 2px, or let's say omega omega, let's say omega omega tau tau. Okay, so that is a relation. So this relation, that is we have learned in the previous slide. This one. But please put the minus here. If this is remember to the one. So that's very easy. But now we need to calculate a little bit. Now you can see. Okay, let's see here. F omega 1 t replaced by the integration from minus infinity to plus infinity. F, let's say this one first. F tau 2. F tau 2 here. T plus delta t is the same. Nothing changed. Okay. You have E drop omega tau 2 plus E drop omega 2 tau 2. Okay, it's okay. Did you see? Okay, so tau 2 here, tau 2 here, tau 2. Okay, the tau 2 here. Okay, and tau 2 is the integral variable. Okay, we do the same with tau 1, which is also integral variable. However, you have here conjugate complex. Here is also conjugate complex, and here is conjugate complex. It should be plus G omega tau 1. That is plus G omega 1 tau 1. That is 1, and G omega tau is the integration variable. So it's okay for you. So from here to here, actually that's only this replacement. That is more. So we have obtained this results. And anyway, we have a double integration. And each quotation we can move its sign from integration because the integration is systematic calculation. Yeah? So we can change its sign from integration. And now we have this one. So this term remains. This term replaced by this one. Because from the last line, that's which from the last line. Okay? Not from the last line. Okay? We replace to this line. We move to this line. To this line. Okay. Now we have this one. We move this one. Okay. We still have a double integration. Yeah. So from here, I think the battery is in weak. Yeah. Okay, I have no problem. That's so just fine. I have no problem from here. But the battery is almost empty. Okay, now I'm moving from this one to this one. Okay, this herb, this herb is replaced by this herb. Okay, you still have a double integration here. Okay, so from here to here is not integration, it's clear. And from here to here, I made a mistake here. One integration is disappear because here is a direct input. So it takes value only when T1 is equal to T2. Okay. And one integration is should be removed. Okay. So it's correct. And now you have that is the definition of the correlation of the system. Okay. And that is I have explained. We can prove that the frequency correction function is the square transform of the generate profile. Yeah. That's in the morning session I have explained. Also, the time correction function is the Fourier transform of the inverse the Fourier transform of the local spectrum. Now we have this relation. This relation. We have this relation. Please take a look on this relation. You see, have time. We start from the scattering function. I will explain to you what is the scattering function. The scattering function is a measurement of channel. Yeah. When we send only a sinus signal, but we observe the received signal in the both time and frequency domain. Now I show you a picture. This one. So this is a measurement result. This is a measurement result. That I have a measure in Hanover, Germany in 2002. So I did my PhD. So I have with my colleagues in Hanover. We measure the channel. We take an auto. We run around the city and we set with a sign. Not only one character, like this, a single signal. So we transmit the signal like this. F. Right. That is time domain and frequency domain, and the time domain is like this. Okay. So we transmit a sinus signal, but we observe the frequency and the time domain. So we observe like this. That is receiver. So let me set time, set place. That is a receiver signal power. I think if I want to draw, I draw it similar to the picture here. Observe here. S T and then down. Receive signal power. We have a very nice picture. So I explained to you what is a scattering touch. And here the transmitter is transmit a sinus signal. So that is actually that's only a peak. Okay. The only one frequency F0. Of course, to measure signal you need to transmit the signal with the frequency. But to plot the signal, so you can move into the baseband. You just observe the shift, yeah, the shift of the frequency. So it is like this one. Now you observe. So okay. Let's say that is zero, F0. And when we move around the base station, we move around base station, yeah. Then we have a Doppler frequency shift, yeah. And it should have this spectrum, yeah. Like this. F0, F0 plus FP max, and here is F0 minus. I got my point. You have FP 0 here, and plus FP max minus FP max, and FP max is the maximum Doppler frequency. F0 is the frequency. Can you observe here frequency? And FD max is a Doppler. It's a Doppler frequency. Okay. And measurement is measure. Hello. Okay. Measurement results. So we have a Doppler frequency here, and that T. I'm sorry, that's tau, not T. I'm sorry. Tau. That is time delay. Tau is a time delay. Okay. So when the time delay is 0, it means that there is no distance. Yeah. It means no time delay. We have a maximum receiver power. You have a maximum receiver power. This one. That measure that is another drawing. And here for the next part, next reflection part, we have a tau 0, tau 1, tau 1, tau 1, and tau 2. Like this, and we have same same form. We have same form. Same form, yeah. We like this. Also same form. So the thing is the power for the longer distance is smaller than the power to the closer distance. Yeah. It means that for the closer distance you have more power, longer, less power, more longer, less power, more longer, nearly zero. Okay. So the scattering function actually the concept easy, which has been only a sinusoid. Yeah. But you observe in the domain to observe the number spectrum, and you observe here is a time delay. That is the power delay profile. So in this observation, is the observation of the time power delay profile. Yeah, power delay profile. So in this direction, you have a PDF, the power delay profile, and this direction, Doppler spectrum. Okay. So the scattering function reveals you two functions, two information. One is the Doppler spectrum. Sorry, one. The other is power delay profile. So in the summary, we integration of the scattering function is the direction of the frequency domain. Result is the power delay profile. And we integration the scattering function, yeah, in the time delay domain. Result is the Doppler spectrum. Integration means summation. Integration means summation. Okay. So we summation in this direction into the Doppler spectrum. To summation in this direction into the power delay profile. Okay. Okay. Now that's a summary. That's a summary from our textbook, from below paper, from our text and from below paper. Now that we have a scattering function. We have a scattering function. Integration is the frequency domain. Result is the delay power profile. Okay, the delay power profile or delay power let's say delay power profile or delay power rule now. Yeah. And integration is the time delay. Result is the power Doppler spectrum. Okay. You can in the Fourier transform of the PDF, you have a space to see correspondence. You have to see correspondence. You take the inverse Fourier transform of the spectrum power Doppler spectrum. You have a time correlation function. Double Fourier transform of the scattering function result in the autocorrelation function of the chat of the CTF. that's a picture summary relation between the RCF and the scattering function. Actually, this is also very famous. Can also have this information from the bracket below paper. Okay. So you can use this to borrow the channel, to borrow and to compute the channel. Okay. Now I think we have a short break. I think it's too tired with the calculation and integration. So I think that's the most heavy section during my lecture. So we have short break.